So the law of exponential change, basically, it says that the rate of change of any amount, that is the rate of change dy over dt, when you hear a rate, basically there's a time component in it, is proportional basically to the amount, where y is the amount and and t is the time. T is the time. So basically it's proportional to that. The rate of change of any amount is proportional to the amount itself. So where is the amount and t is the time. So basically where you have a constant of proportionality, we can be able to introduce a k. So dy all over dt the same as ky, where k, this one is a constant of proportionality. Proportionality, basically the k. So now from there now on, this one basically is a differential equation, an ODE, whereby we are supposed to do what? To solve for what? For y. Basically, we want the value of y. We don't want to see the dy and the dt. So the only way for us to be able to come and get the y, we shall be able to do some what? Integration. Now, in the last class, I had said that if you want to do some integration, basically we shall group the dy with terms of y and dt with terms of t. So let me first of all cross multiply and see what I'm getting. So if I cross multiply, this is what I'll be able to get. Dy is equals to k y dt, because we said we can't integrate when dt is on the numerator. So I've just cross multiplied to be able to get that. Now this y here is on the side of dt, so I need to bring it on this other side. So the y, I'll be able to bring it this other side. So I bring this y this side, that side. The only way I can be able to do that is by dividing. So dy all over y will be the same as what? K dt. K dt. Now I can be able now to integrate both sides now, because I have like terms together. Remember, k is a constant, so it will not be able to affect the integration. So I integrate both sides here. So when I integrate this one, I'll get ln y is equals to k is a constant. Remember when you're integrating the x, you are getting x. So when you integrate dt, we shall be able to get out a t. In the previous class, we shall get kt plus a constant of, I would say the constant called c, a constant of integration called what? C. But now the problem here now, we were solving for y, but we have ended up with ln y. So we need to be able to do what? To remove the ln. So the only function that can be able to remove the ln is exponential. So introducing exponential both sides, introducing exponential both sides. The e, remember the e, introducing the e both sides, of the equation, because we are saying we want to solve for y, basically the amount. So e ln y will be the same as e kt plus c. kt plus c. Now we had said e exponential ln y, we shall end up just with the y on this side. This other side we shall end up with the kt plus c. But we had said we can be able to use the laws of what? Laws of indices. When you have plus, it's still the same as adding, so it's the same as exponential kt times exponential c. So remember laws of indices. I can be able to go back basically to the same base, so that means I'm multiplying with that exponential c. Exponential c, I'm multiplying with exponential c. So we just separate the two. Now exponential c is still another constant. So remember c was a constant. C was a constant. Hence exponential c will still be out a constant that we can able to give a letter. Let's say what? A. You can call now another constant a instead of having that. Instead of having exponential c, you can able to call a constant a or constant b or constant c, or if you love your name so much, you can able to call it k. No, not k. K we have already used m. It can be any constant. So I can able to have y will be given by exponential kt and then a. Instead of having exponential c, we can able to call it another constant a. And this one I can just manipulate this one. I can able just to bring the a in front. So a will be given by exponential kt. And that is the law of exponential change. Y is equals to a exponential kt. At this particular time, because you are not mathematicians, I will not request you to do what? To be able to cram, not to cram, sorry, to derive the formula. I think if I just be able to remember the formula, that y will be given by a exponential kt, then you are okay. That is the formula for the law of exponential change. Y is equals to a exponential kt. And there are some notes that I gave you. There's a YouTube video. I hope you have already gone through it. Basically, you can be able to go through that. So let me do an example. So have you gotten the, I hope you'll be able to remember this. If you want to do any question on the law of exponential change, we shall be using this one. Y is equals to a kt. Now here, you must be, maybe have to say something about this one. The a, so our main task will be to determine the value of a and k. So our main work is to determine a and what? And k, because those are the constants. If you are able to determine the value of a and k, you can be able to solve any. And basically the a, we get it from the boundary condition. So there's some boundary condition that we shall be given, and basically we shall be able to see. I think I'll just be able to jump to an example I've written here. This is the example I've written. Hope you can be able to see the example. So the example is reading, a biologist initially at time t is equals to 0 puts 100 bacteria in a growth medium. After 6 hours, he measured for 50 bacteria. Find the growth constant k if the growth follows the law of exponential change. We want to be able to solve that. Basically, is a law of exponential change question. So how do we solve such an equation? So you said the first thing is to recall the formula for the law of exponential change. So we recall the formula. So why? Let me give it a bit of a bigger font. Bigger font. You can be able to see a bit better. I think 14 is much better. So what we need first is to recall the formula for the law of exponential change. So the formula we have derived it. People are coming late. This is the formula. So y, I must be able to go back to the pen. So y was given by a exponential kt. That is basically the formula that you need to remember. Y is equals to exponential kt. So our biology at time t is equals to 0. So first of all, I will start with the first sentence. At time t is equals to 0, t is equals to 0, he puts how many bacteria? 100. So the y will become 100. Remember the y was the amount. Remember this one was the amount. The amount from the derivation. So that is the amount. So at time is equals to 0, y is equals to 100. So this is the boundary condition I was talking about now. This one you can be able to get the value of a. So I'll replace how it is. I replace where there's a y with 100, where there's a t with what? With 0, nothing else. And then we solve for the value of a. So replacing, you'll get 100, the same as a. And then exponential, our k, we don't know the value of it, but we know our time is 0. So this one, we shall be able to get what? This one. Any number multiplied by 0, you get the same as what? The same as what? 0. So I'll get a exponential 0. But you know, any number raised to power 0, e exponential 0 is the same as number 1. Laws of indices. Any number raised to power 0 is the same as 1. So instead of having that, I'll have 100 is equals to a and then 1, which signifies that a is equals to 100. So basically, when you're given t is equals to 0 and the amount, basically that one will be the same as the value of what? The value of a. You just have to replace t is equals to 0, t times k. At 0, you'll still get 0, and then you'll get your a to be 100. So my equation has changed now. I've gotten a value now of a. So this is the equation that I had. Y was given by exponential kt. But you know that now our a is 100. So I replace that one. So when you get one of the value of the constants, you replace immediately. Kt. Y is equals to 100 exponential kt. Now I go back now to the question again. I believe there's more information that they've been able to give me that I can be able to solve now for the value of k. Now they're asking for what? After 6 hours, he measures 450 bacteria. Find the growth constant k if the growth follows the law of exponential change. Now, this is now the other now condition that have been given. So the first condition always is to find basically the value of a, or it will be able just to assist you. Now, the second one now will be able to assist me to get the value of k. Because now in my equation, I don't have any other a. I've gotten the value of a. Now I need to use the second condition. So the second condition says what? After 6 hours, he measures for 50. Right, so we come here now. This is the new equation that I have. Y is equals to 100 kt exponential kt. Now, you're saying now the other condition you have been given now at t is equals to 6. At t is equals to 6. At t is equals to 6. He measures how many bacteria? Y, or 50 bacteria. So again, I replace again now in this equation, and just replace the way it is. So where there's a y, I replace with 450, and then is equals to 100, and then exponential k, and then you have been given the value of t is what? 6. So I can be able now, I'll just replace the t's to be 6. K times 6, you get what? So you get 450 is equals to 100 exponential. Can you say 6k? 6k. Now they're telling us to get the value. What are we solving for? They have told us to solve for the value of what? The value of this, whatever I'm marking in green, the k. We need to calculate the value of k. So how do we calculate the value of k now? First of all, I will bring like terms together, the constants together. So I divide here by 100 first of all. I divide here by 100 to remove that one. So I can be able to cancel that one and that one, the 0 and the 0. So I'll end up with what? Let me rearrange. I'll have exponential 6k, the same as 4.5. 4.5. 4.5. Exponential 6k is equals to 4.5. How do you solve for that one? Do you guess values until you get 4.5? No. Now, if you want to bring that 6k down, you'll go back, you remember the relationship between ln and exponential. So when you have exponential, when something is up, you can be able to introduce ln both sides, and you can be able to remove it, the 6k. So introducing ln, I want to bring the 6k down. We introduce ln. Introduce ln because they have a relationship with exponential. Both sides. We introduce both sides. So this one is just basic maths. Basic maths, you learn this one. So I'll have ln exponential 6k will be the same as ln 4.5. 4.5. Now there's a law of logarithm that I hope you'll be able to remember. This law of log. There's a law of log that we need to incorporate there. There's a law that says that when you have a log of a raised to power m, this one is the same as m log a. Basically, the power comes in front. So that's what we shall be able to incorporate. So we shall be able to come. Or what we can be able to do to make our work easier, when you introduce ln here, when you introduce ln to exponential, ln what? Let's say ln e raised to power, let's say b. This one will just end up with the power b. You'll just end up with the power. You can either introduce that law, or you can just be able to say that when you have ln exponential b, you end up with the power. Basically, the ln and the exponential is as if they are cancelling. Yeah, so we just end up with the power. So I'll remain with what? 6k is equals to ln 4.5. So remember, the ln and exponential, they have that special relationship. So I'm remaining with only the power. Now I'm almost finishing to solve for the value of k. So k will be given by ln 4.5 all about 6. If I solve this one using a calculator, that is ln 4.5, then I divide the answer by 6, I'm getting 0.2, let's say 51. And that is the value of k, the value of k that I've gotten. So I repeat again here that when you, let me go up, when you introduce ln both sides, here, because now you want to solve for k, and the k is in power mode, you cannot be able to solve for it. So what I'm suggesting is that you introduce ln both sides, and introduce ln both sides, you will just remain with the what? You just remain with the power, and the other side will remain with ln 4.5. So when you remain with the power, it is easy, because now when you remain with the power now, you'll end up just doing or dividing by 6 both sides to get now the k, to get the k. So that is the first example I wanted at least to be able to do. So I'll do another example to demonstrate that, the law of exponential change. This other example I had written here. Let me make it a bit bigger. We can have 14. 14, yeah. So this is the question. Suppose an experiment population of 15 cases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original medium? So it is following the law of exponential change. So the first thing I'll be able to do is to recall the formula. That is the first step. So the formula was given by y, was given by a exponential kt. We can say that our k and our a are constant. T is the time. T was the time, and y was the amount. the amount of substance that will be there. So let's read the question and get at least some of the things. So the population of fruit flies increases according to the law of exponential growth. That's what we have. There are 100 flies after the second day. So you can be able to, the time we are dealing with days. So you can be able to say, remember now our time is not in seconds or anything, it is in days. Whatever value we get, it is always be in days. So we have a y, the first condition, y is equals to 100 after the second day. So t will be given by 2. T will be given by 2. Then we have another condition, y is equals to 300 after which a day, after how many days? After 4 days. So we have those two conditions. So we said the conditions are basically to assist us to get the value of what? A and K. If you solve for the value of A and K, then you are done with the equation. It is easy as that, solving for the value of A and K. So this one, I'll need to put the two conditions and then I try to solve them together because there's no T is equals to 0. So even if I introduce there, I'll not be able to eliminate one. This is what I mean. Like the first condition, let me replace the first condition and see what we shall be able to get. So at y is equals to 100, t is equal to that. So where there's a y, I'll put 100. And then I'll have a, and then exponential. So where there's a t, I'll have 2k. I've replaced where there's a t with 2, so I'll have 2k. So you can be able to see in this one, I cannot be able to solve for the value of a. Why? Because we have exponential 2k. Exponential 2k is not like the other one. If t was 0, we could have gotten 0k, which will have gone to number 1. But this one is 2k, so we cannot be able to reduce that one. It is impossible to get the value of what? Of a using the first one. So the other one, we are saying that the other condition is 300, and then our a, and then exponential. Now our time changes to what? 4k. So these are simultaneous equations that will be solved. So this one is equation 1. So this type of equation is not like the other one. So don't say that every equation will be unique. So this one we need to solve this one. If you want to solve for the value of a and k, these are simultaneous equations that we need to do to solve them together now. Because without the other one, you cannot be able to solve the other one. So you need them. So how can we be able to solve them? So let me go back to the class and ask, how are you solving simultaneous equations? How are you solving simultaneous equations? I'm asking, we normally divide. Dividing the two equations is easier, is much faster when you have multiplication, because we cannot we don't have any addition, any subtraction. So I'll recommend we divide. So dividing equation 2 and 1, we divide. Dividing. Two with 1. So let's divide. So dividing the way it is, we have the equal sign. So I'll take the bigger divided by the small one. So I'll have this side 300. So I'm dividing. So I'll have 300 here, all over 100. Then this other side is equals to, I'll have a exponential 4k all over a exponential 2k. So I'm just dividing, and remember the is equal sign, you can be able to see it is still remaining. So 300 divided by 100 on the left hand side, then whatever that I have, a exponential 4k on that side. So let me simplify this one. 300 divided by 100, that is easy. So this one I can be able to cancel like that. So I'll remain with 3. I'm able to cancel the a and that one. Now, what is exponential 4k divided by exponential 2k? Go back to the laws of indices. When you are dividing and you have the same base, I can be able to subtract the power. So this one is the same as exponential 4k. I'm dividing, I can subtract the power 2k, which I will end up with what? Exponential 2k. So under the same base, laws of indices are coming in handy. Laws of indices are coming in handy. When you're under the same base, you can be able to subtract the power. You are allowed. So let me interchange. So exponential 2k is equals to 3. So how shall we be able to solve that equation? Is just the same way I had solved the other one. Philomena, Kiprotich, how will I be able to bring the power down? It's only the only function. So let me do the way she has said. So I introduce ln. So I'll have ln exponential 2k is the same as ln 3. Only that. And we said when we reach there, what shall we be able to get now? So we need now to be able to, we said what, ln and exponential, this one we reduce to like number one. So you'll end up with this side with only the power. So you'll end up with 2k on that side is equals to ln 3. That's the reason why we're introducing the ln, because on the left hand side, we shall end up with only the power. Let's solve for k. So k will be given by ln 3 all over 2. I go back to my scientific calculator. ln 3 divided by 2. So I'm ending with the 0.549. I can be able to work with that 0.549. 0.549. That's what I have. So I've gotten the value of one of the constants k. Now I need now to go back and get the value of one of the constants a now. So remember we are solving for two constants. That's what we said. So I'll be able to use one of the equations. So you can either use equation 1 or equation 2. So let me use equation 1. So using equation 1 to get a. That's what Philomena had said about substitution. So it will be able to work. You substitute back the value that you have gotten. So equation 1 was saying that 100 was given by a exponential 2k. Even if you use the second equation, you should be able to get the same thing. So this one, I'll just input the value of k that we have gotten. So 100 will be given by a exponential 2 and then times 0.459. So 0.459 times 2 is 1.0. I'm getting 100. I'm getting 100. We're going to multiply that one by 2. I'm getting 100 is equals to a exponential 1.098. That's what I'm getting if I multiply by 2. Now, this one is very important. I wish anyone with a calc, someone to get for me the value of exponential 1.098. Because now you may have a calc and you don't know how to use it. So at least I have explained that one. So at least she has gotten it. So let's continue. So when you do exponential, that one, I think the value she was getting was 2.99. You can use 82. Let me just use 82 kindly. 82. So here now I need the value of a. So if I need a, this is 100. So a will be given by 100 divided by 2.9982. Let's see what I'm getting. 100 divided by answer. I'm getting 33 point what? 0.35. 3.35. So that's what I'm getting now. So I'll go back to the law to the law of exponential change. I've gotten all the constants. They were telling me. Let me go back to the question. At least you see the question what they were asking. Suppose there are 100 flies after the second, so we got two equations. Approximately how many flies were in the original population? So that's what they are asking. So I'll again repeat the law of exponential change, the equation. I've gotten the value of a, I've gotten the value of k, and I'll be able to substitute. And then I'll be able now to get the value at time t is equals to 0. The original population, and only how many flies were in the original population. The original population, we shall assume it is at time t is equals to 0. Time t is equals to 0. So let me repeat back again the law. So y, this is the equation that we had. The law of exponential change, y. We've gotten the value of the constants, a, exponential kt. Y was given, our a, we are given as 33. Can I remember 33 point what? 33.35. And then our k was 0. Let me see. Our k go up 0.549. 0.549. So 0 pence. 0.549. And then I have the t now. So they are asking originally. So you can able to assume originally it is at t is equals to 0. So original basically is the time you put the bacteria. So we shall assume at t is equals to 0. So we replace back there that value. So we shall get y is equals to 33.35, and then exponential 0.549 times 0. Any number raised to power 0 will always be 1. Any number raised to power 0 will always be 1. So here we shall just end up with y will be given by 33.35 and then exponential 0. You see the exponential 0 is always 1. So here the answer will be what? 33.35. So they were asking approximately how many bacteria there were. Now, in bacteria, we cannot be able to say we had 33.35. When you come to human beings, to animals, to bacteria, insects, we don't deal with decimal places. So we can only be able to round off this answer. So we round off this answer, and I believe the best for us to be able to round off, because we don't want to exceed what we had before, approximately, because we had 35. Can always assume that our initial amount was what? We round off down 33. Can only assume that we had less bacteria, because when you have more, you'll be able to exceed the number that they had been able. So approximately, you can be able to say there were 33 bacteria that were there. Why? Because in animals, we don't deal with decimals, or insects, we don't deal with what? Decimals. So that's how you get. So you can be given an equation, and then given the boundary conditions, you solve. And basically, for the law of exponential change, I recommend you to divide the two equations, then you solve for a and k, and you'll be okay. Sawa. Oh, sawa. Wawira, Chris-wise, you got it. That's okay. Sawa. So let's do. We go back to now the final example. I do the final example. Final example. This is here. This is what we have. A biologist puts 200 bacteria. Increase the font. A biologist at time t is equals to 0. He has that number of bacteria. After 5 hours, he measured 600 bacteria. Find the growth constant k. The growth follows the law of exponential. Find the number of bacteria after 8 hours. So again, this one, it is almost the same as the first example that we did. So I'll first of all start with the law of exponential change that we derived. People can be able to follow up the video. So y is given by a. Just remember the formula kt. Now, our biology is initially at t is equals to 0. The bacteria are how many? They are 200. So remember, at when t is equals to 0, you can be able to get the value of a. I have said it. At t is equals to 0, that is the only condition that will be able to give you a. There's no other condition. So if I had t is equals to 2, maybe I could have solved two simultaneous equations at the same time, like the previous example. So when you have t is equals to 0, I guarantee you will be able to solve for the value of what? For the value of what? For the value of a. So I'll just replace first of all to solve for the value of a. So 200 is equals to a. Our K we don't know, but we know the value of T, which is 0. Then I'll end up with A. Any number multiplied by 0 is 0. Any number raised to power 0 is the same as 1. So this one will end up that A is the same as 200. You can be able to see. When you have T is equals to 0, you'll be able to eliminate the K, because when you multiply K times 0, you'll get 0. Any number raised to power 0 is 1, so A will be given. So I'll go back to my equation and replace back the value of A. So I'll have this one now. 200 exponential kt. That's what I have. I go up, we see what we are solving. So they are saying the second condition, after 5 hours, he measures 600 bacteria. So the second one will be able to assist me now to get the value of K. So after 5 hours, he measures 600. So let's go now. After 5 hours, after T is equal to 5, after T is equal to 5, at T is equal to 5, he measures how many bacteria? Why? 500 bacteria. Is it like so? No, 600, sorry. 600 bacteria. He measures 600 bacteria at T is equal to 5. He measures 600 bacteria. He measures 600 bacteria. So I replace now. Again, replace to solve for the value of K now. So this is 600 is equals to 200, and then exponential. The value of K is not known, but the value of T is known. That is 5. So I multiply K times 5. I'll end up with 600 is equals to 200, and then exponential 5K. Now, if you want to solve, we are solving a number for K. That's what we want. That's the remaining constant. So how do you solve for this one? I'll bring like terms together. So first of all, I remove this 200 this side. I divide both sides. I remove the 200 like that. I cancel. This one 6 divided by 2 remain with 3, and then exponential 5K. So when you reach there, I'll ask again, how can we be able to solve for K? Let me start with Chris Wise. Chris Wise there. That is very important. So introducing ln both sides. So this is what I have. Let me rearrange. I'm just rearranging, but I'll have the same thing. So I'll introduce ln both sides. Introducing ln both sides. We are putting ln so that at least we can be able to bring the 5K down. This one will be given by ln 3. And we said ln exponential. When you have ln and exponential, you'll end up with only the power. So you'll end up with 5K this side, and then ln 3. So K will be given by ln 3 all over 5. And go back to the calculator. ln 3 divided by 5. I'm getting 0.2 and say 22. 0.22. That's the value I'm getting. So I've gotten the value of K, I've gotten the value of A. I'm in a good place now. So find the number. So find the growth constant K if the growth follows the law of exponential. We have gotten that. The final question they're asking is to find the number of bacteria after 8 hours. So I'll go back now to the whole equation now, replace everything, and then I try to find the bacteria after how many? After 8 hours. So our equation was given by this one. Let's repeat. The equation was given by this one. Y was given by A, exponential kt. But we have gotten the value of A to be 200. And the value of K is there up. So Y will be given, this is now the equation that I have, exponential 0.22t. So that's the equation that I have. So you cannot be able to substitute any value, get the value of any amount if you have not calculated the value of K and the value of A. That was the reason. So now the question is asking, what is the amount after how many hours? After 8 hours. After 8 hours, this is our t. So I replaced back the value of t there. And then I saw for 8 hours, I want to see the amount. So y will be given by 200. And then exponential 0.22 times what? 8. 0.22 times 8 times 8. I'm getting 1.76. So y will be given by 200 exponential 1.76. 1.76. So I'll do 200 times shift exponential is under ln 1.76, and I'm getting 1162 point, let's say 49. The answer that I'm getting exponential 1.76 times 200. Yes, I'm getting that number of bacteria. But we said for the number of bacteria, they are like human beings. We cannot be able to work with decimal, so I will round off backwards. And I'll be able to get 1162 bacteria, approximately 1162 bacteria. Please don't round off to the next in whole number. Round off to the previous whole number. To the previous whole number. Yes. So that's how we do it, basically, for the law of exponential change. The law of exponential change. So you round off. You don't round off to the next, but the previous whole number. Anyone with a question? I'm done. 40 minutes.